So we now have a way of turning functions into power series, and so we want to be able to work with these power series here. So we have some operations that we can do with power series. Now, even though a power series represents an infinite amount of terms, we can say this. If f of x is this power series here, and this represents an infinite summation, a sub n, x to the n, and g of x, we'll call that b sub n, times x to the n. So these are power series. Well, if we want to find f of kx, well, that just means we can just put kx in for that. And if we put kx in for x right here, we get the sum of a sub n, and we get k x to the n. And that n affects the k and the n, and it looks like this, another power series. All right. Well, what if we have x to the n? Well, in the same kind of way, we can just swap out the x for the x to the n. So this becomes the sum of a sub n, x to the capital N, and that's to the little n. And we know power to power becomes that. So that's all that's going on. In other words, we're just putting this in place of this x. Well, what if we add these two things? Well, this is just a summation of a whole bunch of terms, and this is a whole bunch of terms. So if we lined up the first terms and the second terms and the third terms, well, it would be the first a sub n term plus the first b sub n. And then the second a sub n term, so on and so forth. And so, in other words, it's just a sub n plus b sub n, or minus if we were subtracting, and then times x sub n. So in other words, term by term, we're just adding the coefficients. It's really all that's going on. So in other words, we can use these power series. Well, here we have a fraction that's not really in that form, that's ready for a geometric series, but we can use some partial fractions to split this up. We can say, well, I've got f of x, which is 3x minus 1 over x squared minus 1, which is 3x minus 1 over x plus 1 times x minus 1. And we can say that we would like this to be sum a over x plus 1 times, or plus some capital B value, x minus 1. All right. And if we clean that up and get a common denominator, we could say, well, that's a times x minus 1 plus b times x plus 1 all over x plus 1, x minus 1. All right. So in other words, we're saying that this is equal to 3x minus 1. Let's do a little bit of work with that. Remember this partial fraction stuff. Ax minus 1 plus bx plus 1. And we can say, well, if x equals 1, then we can plug it all in here. We get 3 minus 1, which is 2. And if x is 1, this goes away, and we have 2b. So that tells us b equals 1. And then we can say, well, what if x was negative 1? Well, if x was negative 1, then that would give us negative 4 on this side. And that would give us negative 2a. And then the b would go away. That should be an arrow there. So that tells us that a is 2. All right. So all that to say, we now have f of x can be written as 1 over x plus 1 plus 2. Oh, I'm sorry. I wrote that backwards, huh? So that should be 2 there. 2 over x plus 1. And b is 1. 1 over x minus 1. Well, we'd like this to be in the form a over 1 minus r. So let's rearrange this here. So this can be, let's say, 2 over 1 minus negative x. That's the same. And then this is, well, let's multiply this by negative 1. and multiply this by negative 1 on top and bottom. Then we have negative 1 over we can go ahead and add those together as we just saw up above, and that's going to be just 2. Oh, wait a minute here. We got to rearrange this a little bit. This is 2 times negative 1 to the n x to the n. Got to do that first. So this would be 2. Let's see. There it is. 2 times negative 1 to the n minus 1 times x to the n. All right, and there is our simplified series for that. Okay? Since x is the ratio here, we know the absolute value of x is less than 1. That means that the radius is 1, and the interval is from negative 1 to 1. Okay? All right, so that's the idea, all right? Now, if we have other functions like this, we got the natural log. Well, the natural log of x is centered at 1. If we want a power series for this, we can use its derivative. So we know the derivative of natural log of x is 1 over x. And we know that this 1 over x is the sum of 1 minus x to the n. We found that out in a previous example. And now if we take the integral of this, so if we integrate this here, integrate both sides here, we get the natural log of x equals, and if we integrate this here, we're going to get the sum of, you're going to add 1, n plus 1, minus x all over n plus 1. So there we have a series, 0 to infinity, that represents the natural log of x. Okay, and we can do the ratio test here to find its interval of conversion. So we're going to do our ratio test here, which is a limit of the absolute value of the n plus 1. Well, notice it already is n plus 1, so we need n plus 2 over n plus 2, plugging in n plus 1 there, divided by the nth term, which means times the reciprocal. All right, we know the ratio test there. And what happens here? Well, if we subtract these minus these, leave us with one of them. So we have the limit as n goes to infinity of, we have 1 minus x times n plus 1 all over n plus 2. Okay, so this is going to be, let's rewrite this, you might see it a little better. N goes to infinity. The absolute value, I'm going to distribute the 1 minus x. So we have 1 minus x times n plus 1 minus x times 1 all over n plus 2. Well, these things at infinity are going to go away. And n over n, so n is the variable that's changing here and going to infinity. So we're just left with 1 minus x. So the absolute value of 1 minus x, which has to be less than 1 because of the ratio test. And what that means is that we have the distance between 1 and x is 1. So this is our center, centered at 1, and this is our radius. So x is going to be between, centered at 1, we're going up 1 to 2 and down 1 to 0. Okay? All right. And so that means our interval of convergence is 0 to 2. Now we do have to check the bounds here, the to see if it converges at the boundary points. So if we plug in 0 here, we get 1 to the n plus 1, which is going to be 1 over n plus 1. That's a harmonic series that diverges. So when you plug in 0, this does not converge. It diverges. What happens if you plug in 2? Well, if you plug in 2, the other boundary point here, then we have 1 minus 2, which is negative 1. And then we end up with this series, negative 1 to the n plus 1 all over n plus 1. Does that converge? Well, that one does, because it's alternating. Remember, if it's alternating and if you take that negative 1 out and the leftover 1 over n plus 1 goes to 0, then the whole thing converges. So alternating sequences converge easier than non-alternating. All right. So 2 does converge, so we've got to come over here, and our interval is going to be including 2. Okay? All right. Last but not least, what about a series for arctangent here centered at 0? Well, we know that the derivative of arctangent, so if f of x is arctan, let's see, let me erase this here. There we go. If the derivative is arctan, then f prime of x is 1 over 1 plus x squared. Again, we defined f of x as arctan here. So we need to look at a couple power series here, first of all. Well, we know 1 over x. We found that so far. And that was 1 minus x minus 1 to the first plus x minus 1 to the second plus or minus x minus 1 to the third, so on and so forth, that alternating sequence there. So if we do 1 over 1 plus x, we're going to plug in 1 plus x everywhere there's an x. And if I plug 1 plus x in here, then we have 1 plus x minus 1. And that's just an x. So it ends up being 1 minus x plus x squared minus x cubed plus x to the fourth dot, dot, dot. Pretty convenient, huh? Well, if we now change this a little bit further, 1 over 1 plus x squared, well, now we're going to take this x squared. See, the only difference here is I've got an x squared in place of x. So everywhere that I have an x here, we can put an x squared. Okay, and so that gives us 1 minus x squared plus x squared squared, which would be x to the fourth, minus x squared cubed, which would be to 6, x to the eighth, so on and so forth. So it's alternating, and it's those even ones there. Okay, pretty interesting. So that's 1 plus x squared, and we know that if we integrate that, then we can write the general term. This is the sum of, we got an alternating sequence here. So we have x to the, let's see, we've got n equals 0 to infinity. So we have x to the n plus 1 divided by n plus 1. That's, actually, we actually got 2n plus 1. These are odd numbers. So we have 2n plus 1 and 2n plus 1. And we have all of that times negative 1 to the nth power. Okay? Negative 1 to the 0 power is positive 1. Negative 1 to the first power is negative 1. Negative 1 to the, what did I say there? Negative 1 to the first, negative 1 to the second power, negative 1 to the third power, so on and so forth. And double check, this is x to the 2 times 0 plus 1. 2 times 0 plus 1 is 1, so it would be x to the first. Plug in 1, we get 3. Plug in 2, we get 5. Okay, there it is. We found it. Great. So that is f of x, which actually we should say this. This is arctan of x. Okay. All right. So now the question is, what is the radius of, or the interval of convergence? So let's find our interval. Doing our ratio test. So we have the n plus 1. Okay, the n plus 1 is going to be, so limit as n goes to infinity of the n plus 1, so that'd be x to n plus 1 all over 2 n plus 1 plus 1 divided by the nth term, or times the reciprocal, 2n plus 1 all over x to the 2n plus 1. Cleaning that up, we get x to the 2n plus 3, distribute that 2 and add the 1, all over 2n plus 3, times 2n plus 1, all over x to the 2n plus 1. Okay, what happens here? Well, we have subtract the exponents here. 2n plus 3 minus 2n plus 3 minus 2n plus 1 will leave us with 2. And these don't cancel here. Nothing cancels there. So we end up with limit as n goes to infinity of x squared times 2n plus 1 over 2n plus 3. Okay. And so last but not least, this goes to 1 here. So that leaves us with the absolute value of x squared. And that has to be less than 1. And so this means that x is going to be between 1 and negative 1. Or our interval is 1, negative 1. Let's check our endpoints, 1 and negative 1 here. So when this is 1, we're going to get something like this. The sum, when x is 1, then we're going to have negative 1 to the nth over 2n plus 1, and that converges. When x is negative 1, well, we get negative 1 to the 2n plus 1 power. So that would be plus times another n. We're going to get the sum of negative 1 to the 3n plus 1 power all over 2n plus 1. And this is still going to be alternating. Okay, watch what happens. When you plug in 0, you get 1. When you plug in 1, you get 4, an even number. When you plug in 2, you get 7, an odd number. Plug in 3. Okay, it's going to keep alternating. So this actually alternates. So this is an alternating sequence also. This converges also. All right, so it converges at both. So our interval of convergence ends up including both of these. So our interval is going to be 1, negative 1. All right, so that's how we develop these. All right, in our next lesson, we're just going to be using these. We've got these power series. We're going to memorize some of them, not necessarily all of them, but we're going to use them, and we can see now how they're real handy because these series can just build off of each other, kind of like we did over here. We started with one series and we changed it, and we got a bunch of different series that are all just connected. So we don't have to kind of go back to square one anymore. So, all right, well, there you have it. That's the idea. Again, these operations are real important because they give us a lot of shortcuts. Shortcuts are great. So, All right. Hope that helps. Thanks a lot.